exciting. Before I start with my formal presentation talking about water extraction on extraterrestrial bodies, I'll give you a quick overview of Honeybee Robotics. We are around a 50-people company based in New York City, Denver, and Pasadena. I'm based in Pasadena. I love it. It sort of reminds me of, it's like Sydney. I think Sydney is very nice, probably nicer. What we do is we cover a lot of extreme environments, going from Mars and Moon. We are actually present on Mars exploration rovers, the Phoenix mission in 2007, and also on the Curiosity rover. We do a lot of aerospace stuff, defense, and also mining. We actually developed some of the robotic systems for Rio Tinto Mine of the Future. We do a lot of subsystem level hardware. This is, for example, innocent looking electric motor, but this motor was designed to work at 500 degrees centigrade. And the reason for this temperature is driven by temperature that's on the surface of Venus, 500 C and almost 100 atmospheres. And we also have end-to-end capabilities. So in my office, we can draw up on a napkin sketch, and a month later, we have actually a hardware that we can test in the vacuum chambers. For those of you who are still skeptical, this is the slide I showed 2 days ago. I'll repeat it here. New York Times, October 9th, 1903, over 100 years ago, the flying machine, which is an airplane, which will really fly, might be evolved by the combined and continuous efforts of mathematicians and mechanicians in from 1 million to 10 million years. If you look at the Wright brothers' diary, same date, we started assembly today. All right, so you can be really wrong. And if you look at how technology has evolved in the past 100 years, it's just unbelievable. All right, so why do we need gas stations? Everywhere you look, there's plenty of gas stations. And the main reason is that your tanks don't have to be the size of the car. So you can traverse 100 to 200 miles where you refuel it and you carry on going. If you go across the outback, obviously you have to bring jerry cans, you have to put additional fuel tanks and stuff like this, which means you can bring less stuff with you. And also carrying more fuel means you become very inefficient. Your efficiency actually drops. It's the same thing with airplanes. This airplane doesn't have to land all the time. There is an airborne refueling station, depot, another airplane that refuels this one. This one is, a very important one. So to cover, traverse long distances. So you don't want this guy to go back and forth, refuel and fly, and carry on flying and so on. So why not doing similar thing out in space? This is based on this drawing. You can see this is not a new idea. People have been talking about refueling in space for a while. And since the 90s, there has been a steady technology development to show that refueling in space actually is possible. So Boeing, under DARPA funding, showed autonomous docking and refueling. Just recently, actually, on the ISS, we've been also showing the autonomous, with the Dexter robot, autonomous docking and refueling. So this technology progresses, slowly, and the future, in my opinion, the future is bright. But what you need for a refueling station is fuel. And the fuel can be, in my opinion, water, hydrogen, and oxygen that you either bring from asteroid or from the surface of the moon. So my presentation deals with the fuel part. How do you actually mine the water and bring over to these fuel stations? And what is everywhere? And one thing you can use, obviously, on the International Space Station for human consumption. The big one is radiation. Water absorbs all this radiation in space, so protects our presence, and obviously fuel. This is a big business because once you use up fuel, you have to replenish it. For radiation, this water doesn't go anyway. and water for human consumption, probably around 90% you can recycle. So the only one that has actually business case is fuel. If you look at Mars, for example, initially we thought that water is only in the polar regions. This is a picture of a Phoenix lander back in 2007. That's this lander. We actually built icy soil acquisition device, and Renee's previous company built this robotic arm right over here. When the Phoenix landed on the surface of Mars right over here, the rocket thrusters excavated the first 2 inches of a regolith and exposed vast ice layers. So if you take a brush and brush off this regolith, what you're going to find is pure water ice. So there's plenty of water ice on Mars. Just recently, what we found is that if Viking 2 had a scoop that could dig deeper, it could have also found water ice back in the 70s. The data showed that there are regions of Mars closer to the equator that has water ice around 0.5 meter below the surface. So you no longer have to go to the polar regions. You can go to like 40 degrees north and excavate water ice. There is also quite a bit of water on the surface of the moon in the polar craters. Just recently, I read a paper that claimed that Soviets had their sample return missions in the 70s. They actually drilled down close to 2 meter depth to acquire a sample and return the sample back to Earth fully autonomously. And they found that there is around 0.1% of water on in these samples. No one actually heard about it because it was written in Russian in '78, and only recently people start translating these magazines. But if you look at in the past decade, 2 decades, there has been a steady influx of new spacecrafts looking for water, and everywhere you go, we find high concentration of hydrogen, which we think is linked to water. And obviously asteroids. 2 companies recently have started to look for asteroids that have water, carbonaceous chondrites, and mine this water for for fuel. So how would you mine water ice? There is no water ice in the ground in Los Angeles. It's just too warm, so it's like in Australia. So what we do is we go to the Arctic and also Antarctica to learn how would you dig up the formations that do have icy water ice. So this is a picture in the Arctic a few years ago. This water ice just underneath this broken up breccia is what a liquid deposited. So a liquid kind of went through this layer and the ice top and formed the icy formation. It was, once we digged out this dry stuff, we couldn't really dig into the icy soil. It's essentially as hard as concrete. Even you can see the guy with the pick. That's me actually sitting supervising. We also go to Antarctica, and Antarctica is slightly different from the Arctic. It's more like Mars in that you don't have liquid water. So this glacier that you see right over here, an icy formation underneath was vapor deposited. It's like vapor that you find in a freezer. It's the same way. So ice was formed like this, probably on the surface of Mars. I'm sure upon the moon. But in Antarctica, this is a perfect analog because if this vapor deposition created some kind of different ices, this is how would you test it. So again, if you take out this desert pavement, which is kind of desiccated layer, you get into this ice-cemented ground, and we also found it to be super hard, almost as hard as concrete. We couldn't even break it up with like rotary percussive chisel system. We also did a bunch of tests in a lunar simulant JSU-1A at -20 degrees centigrade. That's our solvent with compacted JSU-1A at -20, and this is a percussive scoop the size of the scope is the same as the survey scope that was launched in the 60s. And we use percussive systems to reduce the excavation forces. And this is actually a movie that shows a percussive being lowering down into this icy soil. That's a survey scoop. You can actually hear the percussion kicking in. And you're not going very fast, not mentioned. And the idea is obviously to go down and traverse across, so this bed could actually move to the side. And what we found is that around 3,000 newtons, it's 300 kilograms, you couldn't really go very far. So why this, sort of, one would think, conventional digging approach fails? Well, if you look at the strength of the icy soil as a function of temperature, it gets to hard concretes. JSU-1A, folks at Orbitec looked at the strength of JSU-1A with different water concentrations at LN2 temperatures, and if you fully saturate it, you're hitting the strength of basalt. So obviously, no one goes with a shovel and digs into the rocks. So this approach of going into the icy soils on the moon, or Mars, or maybe even asteroids, is no go. Also, if you look at the pure ice as a function of temperature also increases in strength. So this is 100 MPa. This is the strength of a rock, basaltic rocks. So when diggers fail, drilling system actually work. You guys here do a lot of mining, and with a lot of blast hole samplers and drills out in the outback. And these big drills, they just plow through iron ores like if it was nothing. So we did a similar thing in the Arctic. Once we dig out the hole, then we try different augers, different percussive drills. And actually, as a function of bit diameter, you can predict penetration rate really well. And it was pretty easy going. So, in the Arctic, this stuff works. In Antarctica, we also did a lot of drilling with the icebreaker drill. It was a fully autonomous drilling. What we actually found, because Antarctica is so dry, look at this soil. This is ice-saturated soil and behaves essentially as sand. So as long as soil is kept at very low temperature and the atmosphere is pretty dry, this stuff you can sieve as if it was essentially sand on a beach. And also we drilled into JSU-1A a few times. It was also easy going. Nice thing about drills is that based on the energy, you can predict the strength of the formation. So if I know I need 200 watt-hours per meter of drilling, based on the empirical data, this strength is around 60 MPa, and from that I can back correlate the fraction of water in a formation. The same is true for penetration rate. Once I have empirical data based on the penetration rate, I can tell you how much water was initially present in the formation. So it's a powerful technique for giving you extra information. What happens is when you drill, so this is a phase diagram of water. That's pressure right over here, temperature is right over there. And Mars atmospheric pressure and temperature essentially brackets triple point. So what is very unstable? In certain regions of Mars, essentially water sublimes right away. In the northern polar regions of Mars, when pressure is slightly higher and temperature actually reaches around 10, 20 degrees centigrade, water could be present, but it's very unstable. If you look at the moon and asteroids, what is, the pressure is pretty much vacuum, so you're not going to have a liquid water, it's going sublime. So for my PhD, I did a lot of drilling experiments under Mars conditions in icy soils, in icy rocks, in dry rocks, even in muds. And what I found is when you drill in icy formation, the heat generated by the drill bit in a rock is used up by latent heat of sublimation. So this icy water sublimes and blows the cuttings out of the hole. So this is similar to air drilling on Earth, except you do not bring gas with you. You generate gas, or in this case, water vapor, during a drilling process. When you do this, so this is a power during drilling, and that's a penetration rate. When you stop the sublimation effect, you're essentially going to slow down drilling, so you don't generate heat. The power triples, penetration rate drops. So the sublimation effect essentially helps with the drilling process and makes things very efficient. These tests were done in a small vacuum chamber, but we also had a 3.5 meter vacuum chamber in Pasadena, where we do full-scale drilling down to 1 meter depth in different formations and also different temperatures. This is a cooling coil. There are, in general, two approaches to extracting water. In the first one, it's a traditional mining approach. You mine something, and then you deliver your feedstock into a reactor where you do crushing, processing, and so on. So there is a time required to take something out, transport it, and deliver it. And that's how the mining industry essentially works. So in this case, here we have a rotopercussive drill deployed from a 3 degrees of freedom boom. We acquire the sample, and then we position, by the way, this is fully autonomous operation. We deliver a sample straight into our reactor, which in this case is essentially a cup. And then you go back into the same hole, and you carry on acquiring more and more samples. By taking these short bites, actually, you can preserve stratigraphy. But that's an approach that we wanted to stay away from. So we developed a second approach, is you bring the reactor to the icy regolith. In this case, you have a deep fluted auger, which you use to drill into the formation, and then the auger moves back into your reactor, and that's where everything takes place. So you don't have to transport it back and forth. So this is operational sequence. That's a rover-based water extraction system. You have a deep fluted auger that's initially preloaded against a surface with the outer tube, the reactor. You drill down, say, 1 meter depth, then you pull auger out with the icy soil on the flutes. You move a foot away, and then you preload your reactor against the surface, creating a leaky seal. And then you pump a heat. The MSL rover has an RTG nuclear device to generate electricity. Generates around 110 watts of electrical power and over 1 kilowatt of heat. So you can tap into this heat and move it into the reactor to sublime water vapor. So as the water sublimes, it condenses on a cold finger, and the soil behind it becomes more dry. And then you lift the outer reactor to exposing dry soil. You spin auger at high speed, and you dump soil onto the ground. So this was the idea. Ideas are great, but you need to show that they're going to work. And that's the next slide will show how we do it. But before I go there, a lot of folks have been also talking about extracting water in situ. So like you drill down, you tap, put down the heat, and you capture sublime water going this way. The problem with this approach is that you have a lot of heat, essentially, that propagates away. So you end up essentially warming up a planet. Also, if the water is very unstable, you create pockets of water vapor. And if the water vapor is above a certain pressure, triple point, you recondense everything. And then when water recondenses back to ice, you can essentially trap entire drill inside this icy soil. And something like this that happened many times in Antarctic and Arctic. You drill down, by mistake, you warm up ice, melts, refreezes, and you can't pull the drill out of the hole. So you essentially, you can anchor yourself to the ground forever. So that's why we moved away from this approach. To show that this approach actually works, we developed a breadboard. So this is a quick sketch. You have deep fluted auger with icy soil. This is a leaky seal, so that's your soil. This is some kind of a tubing and a cold finger. And this is actual experiment inside the vacuum chamber. So that's our cold trap. That's our reactor with the deep fluted auger inside, and that's JC1A, which is our essentially leaky seal. And we've got a bunch of pressure sensors at different points. We have one bunch of temperature sensors as well to measure temperature. And the water vapor comes out through this tubing, goes in, and recondenses inside the cold trap. And everything is done under vacuum conditions. This is another view of the reactor and the deep fluted auger. So that's this auger before it's packed with frozen water saturated JC1A. This is our line heater that actually slides inside the auger. And this is our reactor, which in this case is essentially acrylic tube. When you run the test, when you actually pump the heat into the auger, this is what you see on the outside. The water essentially sublimes. And at one point, this vapor essentially goes out into the cold finger. So this is a progression of a reaction. After half an hour, so you start with this, you end up with clean water, and you end up with a dry soil. And everything is pepper dry, like it's Sahara Desert. So we realized this actually approach works. And then we decided to look at efficiencies and so on. This chart essentially shows all the data that we've been acquiring during the heating process. Probably the most important one is this curve that shows the temperature of the soil. You can see that right here is very low, and all of a sudden it starts increasing. At this point, when you see the temperature of the soil increasing, this tells you that the soil is dry. Right. So the heat is no longer being used up by latent heat. Now it's used up to warm up the soil. So I know if I see the soil temperature rising, I'm going to switch off my experiment to increase the efficiency. Right. For asteroid water extraction, we decided to couple it with our anchoring system. We developed a kind of a bracing approach to anchoring on the asteroids. It's sort of like a climbers in the mountains. When they climb up, they cannot sometimes get a good grasp of going up, so they do this kind of thing and they pull themselves up. So we decided to do the same thing. We had these anchors at a very high oblique angle, and they are driven into the regolith, providing these kind of horizontal forces, which essentially provides a bracing effect for the asteroids. And this is an example of one of these anchors. It's actually a three-tier anchor system. You have this fine point. If you land on a big boulders, this fine, tiny point is going to find a purchase in the small crevices inside the rock. If you land on a boulder field, this deep fluted auger is going to screw itself inside this gravel and find purchase this way. And if you land on a fluffy soil, you have these deep flutes, fins essentially, that again find purchase in a fluffy soil. So you want to explore the surface area. So that's an asteroid landing system. It's essentially like a spider with the anchors. So for water extraction, instead of these anchors, you have our reactors, deep fluted auger at oblique angles. So you land on an asteroid, you deploy these anchors at the same time. The anchors essentially acquire icy soil, you move them back, you do the reaction, you capture water, you dump the dry soil, and you hop to a single place. And then at the end of the day, the asteroid becomes big Swiss cheese. So to conclude, we found that water efficiency, water extraction efficiency with this process is 92%. So we extract 92% of the water initially inside the soil with energy efficiency of 80%, we lose 20%. The power and duration of and dwell time can affect efficiency, and we've done over 60 tests trying to streamline the process. Soil temperature can be used as one way of monitoring drying cycle. When soil temperature starts increasing, you stop the reaction. There are some processes that only melt water instead of subliming it. Soils on the moon, we found it actually. The soils on the moon had a lot of toxic substances, corrosive substances. So one way to eliminate the toxicity from water is essentially to sublime it. So the benefit of going through a vapor transition before recondensing is that at the end of the day you get a clean water, so it's suitable for human consumption, and also a water that doesn't gonna corrode your pipes. A lot of this information and the stuff that we developed for the past 20 years has been written in some of these books. This particular book deals with drilling in extreme environments. It has chapters in oil drilling, underwater drilling, and over 200 pages just about extraterrestrial drilling. And actually, this is the book, and I left it for Leonard. So if you're interested, please, and you can read it. If you have a problem with sleeping, this is also a great solution. And actually, when I was living in New York City, I was writing part of this book, and we went to Central Park with my wife, and asked her to proofread some of the conclusions. And we are laying down in the Central Park. 2 minutes later, I turn around and she's fast asleep. So it works. The other books, they were edited books about Moon and Mars, and they all about mining, ISRU, and I contributed chapters on mining and drilling. And right now we're also finishing a book on asteroids. Should come out sometime early next year, and they also contributed a big chapter around, I think, 40-50 pages that Lena will have to review. So it's also a lot of information. Yeah, there's a lot of data. Anyway, again, these books are here for you to use as a reference. Thank you very much.
So we have a couple minutes for questions. Anybody? Okay. Japanese, Japan. Jane, all the way in the back. The very back. On the right. Hajima.
Thanks. Oh, okay, I just speak loud.
Yes.
Thanks, Kris. Okay, here.
Sure.
Thank you. Hello. About the asteroid, especially the MO, your combination auger and reactor water extraction system works for ice-bearing asteroids such as Canis, which is mainly a main asteroid just beyond the snow line. How about the case for the NEOs?
The asteroids, as long as you have free water, so it's water is separate, it's not in a hydrate, it should work as well. If it's a hydrated water, it's part of the mineral, then obviously you'll have to take it to much higher temperatures. And then again, depends on the type of minerals. It could be really power intensive. The one thing for the asteroids, as you saw, we rely on a leaky seal, and the pressure difference between the pressure in a reactor and the pressure in a cold finger, there is always delta P. That's why vapors essentially trickle down into the reactor. If a seal is too porous, you may find that too much vapor comes on. But if this vapor may come out and also seal, make a seal, so this could, this might work too. But again, we haven't tested it in any of these potential asteroid simulants, so I cannot comment on that.
Up front here.
John.
John, yeah. It's
Good voice.
Yeah.
On Mars, there are, in the regolith, as you know, there are a lot of salts like calcium chloride, magnesium sulfates, which are both very low freezing point depression or very high freezing point depression, and also strongly deliquescent. Have you been able to model or experiment on the effect of these on drilling?
Yes, actually we did. We've been developing an icebreaker mission, which is a mission that would follow in the footsteps of the Phoenix mission. Phoenix essentially scratched the surface of ice, but if you want to look for biomarkers, you have to go at least a meter below the surface, where radiation kind of slows down, so you stand much higher chances of surviving. So after Phoenix discovered perchlorate, we did a lot of tests with perchlorates, ice and with perchlorates, and also icy soil with perchlorates. And there is a small difference in drilling, but we use 2%. I believe Phoenix found around 0.5%. So we are on a slightly higher side. Also, yes, perchlorates do depress freezing point. 1 or 2% is not that much though. You have to go into a higher fraction. Obviously, if you at the eutectic point, you're liquid -70. But we can, before we send something to Mars, we'll probably do these tests. Also, what we do is we have a temperature embedded inside the drill to monitor temperature during a drilling process, and from this infer whether we dangerously close to freeze to melting. And because we don't know whether we're going to have perchlorates or not, which will depress freezing point, we also have electrodes that measure conductivity in real time. And there is also a correlation between temperature and conductivity. So when conductivity starts increasing, which means you're very close to melting something, that's when you stop drilling.
Okay, we need to stop it here. If you want more discussion, Mark,
Kris.
Mark. Kris is,
That's John.
Kris, no, that's John, because Mark is over there, so, he's available out there. We have a break right now. Thank you very much.